Thank you. So I'm presenting the paper From Trash to Treasure, Timing-Sensitive Garbage Collection, which is joint work with my advisor, Aslan Askarov. And to help me with this story, let me introduce you to Bob. Bob's a regular guy who hates doing taxes, yet he still has to compute them. So he asked his friend Alice for help. And luckily, Alice has a program that can do just this for Bob. All he needs to do is just input his confidential information into this tax computation automator. So Bob agrees to do this. And it turns out that the program just instantly leaks Bob's confidential information to Alice, which is bad. So we want to avoid this. And Bob could have done this in a much smarter way. For instance, he could have run the program through some kind of static analysis tool, which would then detect whether or not there are any flows from Bob's confidential information to Alice. And then every time the static analysis tool would say that such a flow exists, he would just not run the program. Yes, he would not run the program. And now Alice comes along with a new program, which is much more complicated. And Bob, as he should, runs this program here through the static analysis tool, which says that he's secure. But it turns out that this program actually also leaks Bob's information through a timing channel. So what the program here does is that it wants to find out whether or not Bob's salary is greater than 500,000. So it measures the time beforehand and measures the time after branching on this information, and then it sends the difference to Alice. And then Alice, based on this number here, can detect whether or not we took this branch in the program, and then whether or not Bob is earning more than 500,000. But we're actually not that worried about such an issue here because there are static analysis tools that can detect such flows, so we can just put on more static analysis to fix this problem. And if we're worried about cache attacks, we can run our program on specialized hardware, which would mitigate such problems. And then the static analysis tool would then detect if these branches on secret information consume equal time, so we don't leak information through the cache. So now Alice is pretty sad. She can no longer leak Bob's information, but it turns out there's another way to leak the information, because the program is running in a managed language. And a managed language has a garbage collector. And we can actually leak the information through this garbage collector. Yes. So here's a program which operates on a stack and a heap. And then as the program moves along, it allocates some memory, and it modifies the heap in some way so that something becomes garbage. Similarly, it can modify the stack like this, and then more stuff becomes garbage. And then at some point, we want to allocate another object, but our heap is full now. So what's going to happen is that we're going to do a garbage collection, which means that we lose some of this garbage from the heap. But the fact that the garbage collection occurs and how long the garbage collector takes to execute tells a lot about the program. So in this work here, we present the first amplifiable covered channel against automatic memory management, which is detectable over a network connection. Then we identified design constraints on the GC, which severely limits the total design space of secure garbage collection. And finally, we show that secure garbage collection can be incorporated with traditional information flow techniques to establish a non-interference result. And all of the meta theory has been formalized in the Coq proof assistant in about 35,000 lines of code. So let me first introduce the covered channel. So here's a program which will leak whether or not Bob's salary is greater than 500,000. So let's first assume that this is true, and Bob is earning more than 500,000 a year. Then what's going to happen is that we allocate some memory and store the reference in A. Then we take the true branch here, which means that we allocate some more memory and store a reference in B. So now notice that A and B, they point to different heap allocations. And then when we get down to the next allocation here for X, we hit the GC threshold here. And since this is Java, there's one thing we need to know about the Java collector is that it runs in a copy collector, which means that the time taken by the GC is proportional to how much memory is reachable in the program. So here we see that there are two reachable allocations in the program, which means that the GC time is going to be fairly large. So in contrast, let's assume now that Bob earns less than 500,000 a year. Once again, we allocate the memory and store it in A. And then we take the false branch, where we allocate some memory and store in C. But notice here now that A and B, they point to the same array, the alias. So when we get down to the allocation for X, we have the situation where A and B point to the same array, and we have some garbage. So now only half as much memory needs to be copied in a copy collector for Java, which means that we'd expect that the time taken by this GC is going to be much faster. And to show that I'm not kidding, I have a demo. So let's see if it's visible. Yes. Okay, so this is the program as on my slides. The only difference here is that I've instantiated size 1 and size 2 with actual numbers, and then I take in Bob's salary as an input. So if we run the program first by taking the false branch here, we get about 10 milliseconds of execution. It's pretty stable. But if we take the other branch, then the time is almost doubled in about 20 milliseconds now. So there's an actual difference in the timing observed from this program here, and this is significant enough to be detectable over a network connection. So here we see a graph of 25 runs of this program here, where we see that if there are no GCs, then the timing is going to be about the same. But when there happens to be a GC, the time taken to GC is much larger when we take the true branch compared to the false branch. So you might be wondering why this is a big deal. We can leak the same thing via some kind of termination channel. But this is a big deal because we can actually amplify the attack to leak any number of bits. So I won't go into details here about what the program does here. You can read about that in the paper. But the important thing is that this leaks a 32-bit integer with a rate about one byte a second. And it produces the graph as seen on the right. And you can do this exact same attack in V8. Which leaks about 1 byte a second as well. So now I've gotten through the first thing, presented the attack, and now I want to present design constraints for secure garbage collection. In particular, I want to ask the question, when is it okay to invoke a garbage collector? And when can you actually collect once you've invoked the collector? So the first observation here is that it's insecure to GC public values when you're in a secret context. So to illustrate what I mean by this, let's consider a program here that starts by allocating memory and store it in X, which we then instantly make garbage. So now we have some garbage memory. And then assume that this secret here, which we want to protect, is greater than 0. We'll now allocate some more memory, which causes us to hit the GC threshold here. And this means that we're now in a secret context, and we can GC the public value, which was previously stored in X. So we GC that one. And then once we get down to the next allocation, we won't do a GC because we've already done that, and we have space enough for that. This time here is going to be small. In contrast, if we don't take the branch, once again we allocate the memory, we make it garbage, and then we get down to the GC threshold this time here. And now we need to do the GC, which we did previously before in the branch. So this time here is going to be much larger. So we conclude that it's actually not safe to GC public values in a secret context. So the natural question is, what about the other direction? And it's actually also insecure to GC secret values in a public context. And to illustrate this, let's imagine we have a Java-style collector as before. So what happens here is that we allocate some memory and store it in X. And then if the secret is greater than 0, we make this garbage. So now we have some memory that, depending on our secret, has been made garbage. And now we allocate some memory and store it in Y, which causes us to go above the GC threshold. And then we do a GC. And now, because no memory is reachable, this GC here is going to be much faster in a copy collector. So this is going to be a short time being outputted here. So as opposed to the other case where we don't take the branch, we allocate the memory and store it in X, and we don't do anything, but we hit the GC threshold again here. This causes us to do a GC again, but this time we need to copy the memory that we store in X because this memory is actually reachable now. So this GC here is going to be larger. This is basically the example we saw in Java before. So it's actually not secure to GC public values in a secret context or secret values in a public context. So this is kind of a bidirectional channel. So with this in mind, let's try and study this problem here more formally. So the idea is to combine a runtime mechanism with some static checks to ensure a non-interference result. And to do this, we've defined a standard while language with heap allocation of arrays so that we have something to GC, and then a command for getting the system clock explicitly, or getting the time explicitly. And this time command here can model any kind of strong adversary, like one that can measure the time by calling the OS, or it can send a remote ping to a server, which would then detect when this ping here arrived. So this language here, they models a isolated study of GC timing leaks, where we enforce control flow leakage via predictive mitigation, where we pad the computation time for high branches. Also, we assume that there are no leaks via cache, because this is a completely separate issue, which has a lot of literature behind it. So let's try now investigate what the runtime mechanism should be for this kind of system here, in order to enforce non-interference. So the idea is that we want to label each allocation with when it's secure to GC this allocation. So here we have the image from before. Now we add the labels to when it's safe to GC these. And you can kind of see these labels, they form a partitioning of the heap, where we have a low partition, which can be collected when PC is low, and we have a high partition, which can be partitioned when PC is high. Also note that we allow reference from low to high, because whatever is going on in the low partition is public information, whereas information in the high part of the heap has gotten there based on secret information, so we won't allow such pointers. So we want to disallow these pointers from high to low, which we do via a type system. So an important constraint where we put on this heap, on this GC mechanism here, is that we assume that isomorphic heaps, they GC with the same time. So it's kind of like the specific values of a pointer doesn't matter, but what we care about is the object graph of the heap, which kind of determines the GC time. So now we investigated what the runtime mechanism should be. The question is now, what should the static mechanism be? So the type system we came up with is a standard Denning-style enforcement for confidentiality, but with a few twists. In particular, we guarantee some kind of integrity result where a low integrity value is a value that has been affected by time. And also, we prevent these pointers from high to low statically, as I talked about before. So let me just take out a few samples from the type system and discuss these. So we have a 2-point lattice for the integrity part, where the bullet means that a value has been tainted by time, and the circle means that a value is untainted by time. So for instance, in the rule for the time command, we require that the variable x receiving the current time must be a value with this bullet here. So for the control flow part here, we enforce that the control flow is independent of time, meaning that every time we branch on some kind of value, we need to ensure that this value cannot be affected by time. And we do this by requiring that the expression E here is independent of time, by saying that it has this white circle type. So if you're familiar with these kinds of type systems, you'll see something different here from the literature, in that we don't raise the PC in the branches of an if statement. And this is because we want to enforce predictive mitigation, where we pad the computation in high branches. So instead of raising it implicitly in the if statement, we raise it explicitly in a command we call the add command. So what the add command will do is that it'll raise the PC to some label L, and then at runtime it will ensure that the branch takes exactly the value specified by the expression E. So the main result of the paper is the theorem saying that a well-typed program, when executed under our secure GC, satisfies termination insensitive non-interference. And to show you how we prove this, let me just talk briefly about the proof technique, because it's interesting. So if we have two configurations, a configuration being a 5-tuple of a command, a PC, a memory, a heap, and the time, which agree on the low parts of this configuration here, which is a detail I'm not going to talk about here, but you can find that in the paper. So if they agree on this, and they both terminate, then there are no apparent relation between these two terminating configurations, but by looking at these two runs, we can construct a new run which terminates in the exact same time as the one on the left and results in low equivalent configurations. So what we see here is that we're really reasoning about three configurations. So the question is, what should the relation be between the middle configuration that we're constructing and the right configuration, which is the one we're given in the beginning? So the left one is pretty simple. The relation between these is the low equivalence relation, which I talked about in the beginning. But for the right one, we need to come up with something else. And for that, we need to go back and look at the type system, because what they need to agree on is the control flow, really. And this is something that is only dependent on the untainted parts of the memory. So we have this interesting concept where the leftmost run and the middle run agree on the low parts of the configuration, which is both, but also the tainted and untainted parts. But the right part of the relation between the right one and the middle one is that they agree on the both the low and high parts of the confidentiality, but only for the untainted values. So with this, we can actually prove the theorem here. So in conclusion, we presented the first automatic memory management amplifiable bidirectional timing channel, which is significant enough to be detectable over a network connection. We've shown that this channel can be closed with standard information flow techniques, which is a type system and a segregated heap. And finally, we've proved all of the meta theory in the Coq proof assistant at about 35,000 lines of code. Thank you.
Thank you for using the term non-interference. That was nice. So I'm not an expert on this, but I've used garbage collecting languages for well over 40 years. And there are a lot of garbage collection algorithms. And I understand that you have a nice type system for dealing with this kind of modal logic, which is great. But does this apply to all memory management systems?
I'm sorry, if it supports what? All memory management systems?
Oh, I'm sorry. Does your channel exist when alternate garbage collection schemes are used?
All right. Okay. So we've demonstrated the attack in the Java copy style collector, and we've also shown that the same attack can be applied in the V8 engine, which runs another garbage collection algorithm. So I don't know if it's possible in all garbage collection algorithms, but I suspect it does. We've only tested it for these two very different collectors. But I expect to be able to do the same attack on any other collector, yes.
Hey, so I have Dan Stefan, UCSD. So what I'm curious, you don't allow for pointers from high to low.
Right.
And that seems really restricting because a lot of programs, at least that I've written, would have that relationship. And I guess there are other ways of potentially solving this problem without that requirement. Have you thought about how to try to tackle that?
So I don't have any answer right away, no. Restricting pointers from low to high is, I don't know how restrictive that is. I mean, it's a pretty standard thing to do in information flow type systems to restrict, to ensure that there are no flows from high to low. So this is basically the same thing, but in a heap setting. So I don't know how restrictive it is, but I suspect that you can actually type a lot of things this way.
Got it. Sorry, go ahead. I'll ask my other question afterwards, or we can talk offline.
Okay.
Hey, Juraj Smirowski, University Bochum. Nice talk, thank you. So, how about using this side channel against real-world libraries? Have you analyzed cryptographic libraries or DLS libraries to use this attack, to use this side channel to execute real attacks?
We haven't investigated any actual library code, because so the setting we're in right now here is that we want to execute untrusted code, but we have no results about how these patterns actually, if they appear in actual code, or if it's just something you can do as an attacker when you want to execute untrusted code on someone else's machine. But it's an interesting thing to look at is are these patterns actually used in actual code so you can exploit them? Yes, but we haven't looked at it.
Okay, let's thank Matthias again.